Just gone 17 minutes to 8 on breakfast. For a decade now, the largest machine in the world has been making major breakthroughs in the world of science and particle physics. The Large Hadron Collider is a giant circular tunnel built underground with accelerators that make millions of particles collide at once. Kiwi physicist Mark Cruz is a professor at Duke University in the US, and he works with the Large Hadron Collider. He's back home for a visit. Kia ora, good morning.
Hey, kia ora. Thanks very much for having me.
Oh, thank you. Can you just tell us, first of all, how did you get to your position as a professor of physics in the US?
That's a long and complicated story, but the short version is I was probably first interested in physics by having a really good teacher at high school. I went to One Tree Hill College, which was then Penrose High School, but it was a really great school for me. Then I got a degree at Auckland Uni, and then went over to the States to do my PhD, and then one thing led to another, and
now you're working with the Large Hadron Collider and a professor at Duke. For people who aren't familiar with the Large Hadron Collider, can you just tell us what it does?
Yeah, so very broadly, we accelerate bunches of protons together, and a proton is an incredibly small entity. I mean, we sort of take it a little bit for granted, but just to give you an idea, we have bunches of protons which are about 1 millimeter wide, and it's about 10 billion protons in a bunch.
Right.
And the protons are so small that if you scale it up to the size, a proton to the size of the tennis ball, even with 10 billion protons in that tiny bunch, the nearest proton would be the other side of the Earth. So when you collide these bunches of protons together, most of them just go straight through each other. So you need about 10 billion of them in order just to hope to get a few collisions, and then by colliding them at these incredibly high energies, we're in some sense recreating what the universe looked like about 1/trillionth of a second after the Big Bang.
That is amazing. We've just been looking at a bit of an animation of the Hadron Collider itself. It's all underground, isn't it?
It's about 100 meters. It's about 100 meters underground. Yep. Right. And so the beam pipes which accelerate the protons, they're surrounded by magnets which you have to use to bend the protons' paths.
Wow. I mean, it is really complex stuff, but I can imagine it's a fascinating area of research. So what are you personally hoping to find out? Well,
yeah, it is complex, but in some sense, you know, the questions we're asking are very philosophical in nature. I mean, why does the universe exist? Why are we here? You know, what is the fundamental reason for anything to exist? But we're using these huge experiments to try to answer these very philosophical questions, and so. And what we find out is there's so much we don't know about the universe. I mean, everything, all our theories and models do quite a good job at explaining about 5% of it. That's everything we see in the universe. There's only about 5% of the universe. There's something called dark matter, which is about 5 or 6 times more prevalent in the universe than ordinary matter, and we have no idea what it is. But it's everywhere. It's everywhere. Yeah. And then there's another more mysterious entity called dark energy, which is causing the expansion of the universe to accelerate. Again, we have no idea what these things are. So there's a huge amount of questions we still need to be able to answer.
This is, I mean, like, I come to work every day. I love my job. You go to work every day and try and work out the meaning of existence. Like, these are profound questions. How does the data present itself to you? Like, because you spend a lot of time at the Hadron Collider, but do you just get spreadsheets of numbers, or what does it look like?
No. So when these collisions occur, they occur in the centers of these huge detectors. And so one of the detectors is called the Atlas detector, which is what I'm part of. And as the particles coming from that collision go through different aspects of these huge detectors, these detectors are read off, and then you have to reconstruct what you think might have happened from that collision. So when you have a collision, anything can happen. Anything that's allowable in nature can happen. So, for example, one of the big discoveries at the LHC was the discovery of the Higgs boson in 2012. Right. So every time you collide protons together, you've got about 1 chance in about 10 billion of producing a Higgs boson. So you've got to, that's why you have to collide them so many times.
And a Higgs boson is like a building block, isn't it?
It's like, the Higgs boson is a manifestation, and it's a crazy theory, and you'd never think that, you know, how we could possibly discover, you know, the manifestation of this theory. But the theory says that there's this sort of 4-dimensional field in the universe, in the very early universe, that then broke down into what we call the Higgs field. A manifestation of that is the Higgs boson. And what this does is that as particles interact with the Higgs field, that's what we ascribe to be the fundamental mass of particles. So now we have the answer to a huge mystery, is how does fundamental mass How is that described in our universe? And now we understand, but we have a lot of other questions that we don't.
Oh, it's amazing. Do many of the people you work with, are they religious or are they spiritual?
It's always a good question.
Yeah.
You know, there's a lot we don't know, right? So I always say, you know, if you ask, is there a God? You know, what is the fundamental meaning of anything? All I say is there is a huge amount we really don't know.
Yeah.
And so you can describe that any way you feel comfortable in doing. I mean, I like to dig a little bit deeper and try to understand more and more. But as you dig deeper and deeper into nature, you know, you find that you don't really know how close to the reality of nature you're really getting. I mean, every time you answer a question, a whole can of worms opens up, a whole other set of questions opens up. So.
That's awesome. Hey, thank you so much for your time, Mark. We really appreciate it. Professor Mark Cruse with us from the States this morning. Amazing to think that you're working in this field from a childhood in Auckland. That's really cool. And we really are answering the questions on breakfast this morning, aren't we? We've had the construction industry, red light cameras, and the meaning of life. So.
And the meaning of life. And now we're going to